Welcome back, Chemistry 30. In the last video we did a couple of examples dealing with rearranging equations to solve for molar concentrations when given the KEQ value and other concentrations in the key item here at equilibrium. Now we'll look at part 2, in which we look at given concentrations not necessarily at equilibrium and figuring out how we can do it. If we can measure the equilibrium concentrations of all the reactants and products in the chemical equilibrium, as we did earlier, calculating the equilibrium constant is straightforward. We simply insert all the equilibrium concentrations into the expression for the reaction and solve. Often we don't know the equilibrium concentrations of all species in an equilibrium mixture. If we know the equilibrium concentration of at least one, though, we can use stoichiometry, like we did back in Physical Science 20, to figure out the others as well. The following steps outline how to do it. So if we look at the next page, I kind of have this, and we'll go through these steps and we'll use them to follow as we go through a couple of questions. And of course we'll be able to you'll be able to do it without using this stuff once you figure out how it works. So key thing here, tabulate the known initial equilibrium concentrations of the species that appear in the equilibrium expression. And for this, I like to call it an ice chart. We'll talk about that. For those species in which an initial and equilibrium are known, we can figure out the change that happened. Okay? And then we can use stoichiometry to figure out the changes in the other species as well, and then use the initial concentration and changes to calculate the equilibrium concentrations, and then we'll be able to figure out the equilibrium constant. All right, so there's two examples we're going to work through. Let's look at this first one. So here we have a closed system. Initially, that's a key thing to note. Initially, we have this and this. So we have 1.0 times 10 to the minus 3 molar of H2 and 2.000 times 10 to the minus 3 molar of I. So let's write, so we can see right here I made this chart up. Initial, change, and equilibrium. So here's where the ice comes into play. So initially, we're going to write down what we have. So initially we have 1.000 times 10 to the minus 3 molars of H2 and 2.00 times 10 to the minus 3. And most of the time, we're putting that into a container, the reaction's happening, so we don't have any products, unless, of course, it says so in the question. Now here, it's at 448 degrees C, allowed to reach equilibrium, so the reaction happens until the concentrations of products and reactants become constant, equal rates, and at equilibrium, HI is seen to be this. So at equilibrium, HI is seen to be 1.87 times 10 to the minus 3. Calculate the Kc for this reaction. So because we know an initial amount and a final amount, we can figure out, okay, well, guess what? I went from 0 to 1.87 times 10 to the minus 3. So my HI concentration increased by this amount. And of course, we initially started with H2 and I2. That got used up to make HI. So here, some H2 got used up, some I2 got used up. Okay? So far, if we look at that little scheme, we figured out the initial and initial part. So now we're at number 3, use the stoich. So we're going to use the change. Use for stoich. So that's what we got. So we can say 1.87 times 10 to the minus 3 moles of HI were produced. And we can see here, for every 2 moles that get made, 1 mole HI gets used. So for every 2 moles of HI produced, 1 mole H2 got used. So 1.87 times 1 divided by 2. And that's going to give me half of that, which is, I'll just write it out here without the scientific notation. Now technically this is molar, but I just put moles here. Maybe I should change that. Molar, oops, well, I'm making a heck of a mess. Molar. So in other words, half as much. So I could say H2 used 0.00094. And do the same thing to figure out this. 1.87 times 10 to the minus 3 molar of HI produced. And for every 2 that gets made, 1 I gets used up. For every 2 molar of HI produced, 1 molar I2 used. So again, half, so it's going to be the same number here. So same thing. So I start off with this, but I used up this to make HI. So what's left over, just simply take 1 minus that amount. 4 zeros there, 60. And 2 minus that, I get that. So now I have the equilibrium concentration. So that's what gets used for KEQ. Use for KEQ calculation. So over here, products over reactants, KEQ equals HI all squared, because I have 2 of them there multiplied, H2I2. H2I2. Okay, so my HI at equilibrium, 1.87 times 10 to the minus 3 squared divided by 0.000060 and 0.00106. So of course, for doing this with a calculator, you could square this, then divide by each of these individually. Just be careful when you do it though, because quite often people do this divided by this multiplied. But remember that they're both in the denominator. So when you do that, you should get 55.0. So that tells us that the products are reactants. We're going to get the products are favored, because that's a fairly large number. It's bigger than 1. All right. So pause the video, turn to the page, see if you can do the next one. The ice chart is set up to see if you can fill in the information and then go from there. Okay, hopefully you had an opportunity to look at this. So we have the formation of ammonia, the initial, key thing again, the initial and the initial. So we have nitrogen and hydrogen in the vessel initially. We threw in enough so that we have 0.32 molar of nitrogen and 0.66 molar of hydrogen. At a certain temperature and pressure, the equilibrium of H2 is found to be 0.30. So here we're told the initial and the equilibrium concentrations of hydrogen. Now we weren't told anything about this to start, but we were told that initially we have this and this, so we can assume that we don't have ammonia in there initially. And so what that of course involves is, well, how much did I subtract here to get 0.3? Do vice versa. Take 0.66 minus 0.3. We must have subtracted 0.36. 0.36 plus 0.3 gives us 0.66. So that's what we have there. So we must have used some of this too, because the reactants have to come together to produce products. The products will increase by an amount. Reactants get used up by an amount. So again, ice. So this, of course, we use this for the stoic and use this for the KEQ calculation. So the 0.36, don't worry about the negative, just simply say 0.36 molar H2 used up, so the reactants get used up. And if I want to figure out how much nitrogen got used up as well, 3 to 1. For every 3 molar of H2 used up, I need to use up 1 molar of N2 used up. Of course, we know if we're doing it right, if we can cancel like that, and then that gives us 0.36 times 1 divided by 3, 0.12 molar N2 used up. So if I used up 0.2, 0.32 minus 0.12, that gives us 0.20. Now do the same thing here. 0.36 molar H2 used up. And for every 3 molars of H2 used up, I produce 2 molar of ammonia. Of course, so there we go. So we have it set up. 0.36 times 2 divided by 3, 0.24 molar of ammonia produced. So 0.24. So if originally I had 0, add 0.24, I got 0.24. That's it. That's the tricky part. It's just filling in that ice chart. But again, you'll be given an initial and final amount of one item. All you have to do is figure out the change and then use that change in the stoich. So KEQ or KC, whatever you want to call it. So products, NH3 to the 2. NH3 to the 2. All over N2. H2 to the 3. So my NH3 amount is 0.24. And then 0.2 of N2. 0.3 cubed, so you have to find your cube button on your calculator. When we do all that, we should get 10.6 repeating. I'll round everything off though to 2 sig figs, so we get 11. All right, that's how you do that. So you started the assignment already, hopefully. You're doing the 1.5 question number 1, just rearranging the equation. So now you should be able to do questions 2 and 3. They involve making an ice chart. I don't give you the ice chart, so you'll have to make that format, fill it in, and then you'll be able to go from there. All right, we'll see you again.